This is free response question number 2 from the 2012 AP exam in calculus, part B. So in part B, our region R that we've been working with is now the base of a solid, and the cross section perpendicular to the x-axis is a square. Now, since we're given here cross sections perpendicular to the x-axis, we do not have the luxury of being able to integrate with respect to y. We must integrate with respect to x. And then we're going to create nice squares standing off here and create a big volume that way. We can try to visualize that, or we can just go ahead and say what the integral would be. Since this is our base of our square s, on this part of the curve, that s is going to be equal to my top curve minus my bottom curve, which is ln x minus 0. Or I could just say that the s, the length of the side of a square, is simply equal to y, which is ln of x. On this side of the breakpoint, the sides of the squares are going to be governed by this function, 5 minus x. So that's my length of my squares, and then of course the area of these squares, if I take a square out, the area of it is just equal to s squared. So there's really two parts to this integral, from 1 to this point A, which I still have in my calculator, as you would when you were doing this question. We still have that point x for the breakpoint in our calculator from the previous problem, if we did with respect to x. Well, so let's go ahead and start setting up the area. The integral. What we want to say is that the volume is equal to the integral from a to b. Normally this is what we say about cross sections, of a of x dx. But this time we have two different area functions and two different sets of limits. So for us, that's going to be the integral from 1 to, and let's call this still a for now, 1 to a, and that area of x is equal to s squared, where the s is equal to ln of x. So that area is going to be ln of x squared dx. And then as we go from a to the other intersect point 5, now the length of the side of the square s is now 5 minus x. So 5 minus x squared dx. So what we've done is set up an area formula for each of those. In this case, we have a square with side length s equals 5 minus x, but since it's a square, we had to square that. And on this side, we have s is equal to ln of x. But again, since it's a square, the cross-section is a square, we had to square that s. So this is our integral. Now, they've asked us to write but not evaluate that integral, that expression. So we don't have to work out what this is. However, I cannot leave that a sitting there. So now I'm going to have to actually write down that number that we got as our intersection point from our graph. And of course, every time I go out of that graph, I'm losing that. But I can just now go calc, intersect, and just go enter, enter, enter. And it tells me that that intersection point, that x-coordinate, was 3.693. So now I can say this is the integral from 1 to 3.693 of ln of x squared dx plus the integral from 3.693 to 5 of 5 minus x squared dx. And now I've written that integral. It asked me not to evaluate it, so I'm not going to. We'll just leave that there, and that's our answer to part B.